Okay, can you guys hear me out there? All right, hopefully you can see the slide deck just fine. So it's actually not Friday, Wednesday, it's September 11th, 2020. So what we will do today is just go through some brief Canvas updates. I'll talk about the laptop loan announcement and then just a refresher on your Module 2 assignments. We'll look at a molecule of the lecture called Crestor. We'll answer a couple questions about that. We'll pick back up with IR that we left off on Wednesday, and then I'll show you some websites where you can get additional spec problems from. So now I have Canvas showing here. So I sent an announcement on the 10th, it looks like, about this laptop loan program for students. So if you're not aware of that and you're in need of a laptop, I know some of you were only had tablets to use, and that can be an issue with the lockdown browser and whatnot. So the USM Foundation, with CARES funding from the federal government, started this laptop loan program. So you can click on either of these links. It takes you to the same thing using your SOAR credentials, and you'll be able to pick up a laptop to use for your classes this semester. So I would say if you do have a smartphone, download the Canvas app so you get those notifications when things change, announcements, etc. And again, just a refresher from Wednesday's announcement. So we're in Module 2 now. When you're clicking into the Wiley Plus resources, again, this is the chapter reading here, chapter 14 or chapter 15. When you're doing the homeworks or the Orions, please click these links directly to take you into Wiley Plus, so that your grades transfer properly from Wiley Plus into Canvas there. So any questions on that? Again, your exam 2 will be Friday, September 25th. That will open at 8 a.m. It will be open for 24 hours. And then close September 26th at 8 a.m. So the same format as exam 1. You'll have 25 questions with 60 minutes to complete them. Any questions on Canvas? Okay, so here is this molecule here. So if you open up your phone app, your photo app on your phone or tablet and scan that QR code, it will bring up a molecule called Crestor. And as you can see from the name on the slide here, this is the formal name of that compound. So Crestor is the brand name that's sold by the company. So the chemical name is actually shown, and you can see it's pretty long. That may look sort of intimidating now, but in this semester, we will learn the sort of algorithm for solving, converting a name into a structure. So I said before, in Western culture, we're taught to read left to right when we're reading anything. And that's how you would read this name. You would start reading this way and, end up at the end to the right. However, when you're looking at a name and you want to convert the name into the structure, you actually start at the end. So let me just highlight here, sort of this region here. When you start at the end of that name, that tells you like the parent carbon chain and what the main functional group is. And so that gives you an idea of how many carbons are in the main chain, what is the parent or the highest oxidation functional group, and this ends up being a carboxylic acid. So it says hept-6-enoic acid. And what that means is there's a 7-carbon chain. At the 6th position, there's an alkene. That's where the E comes from. And the main functional group is a carboxylic acid located at position 1. Again, we'll go through all of that as time goes on, but that's just a preview of what we're aiming to do. So here is Crestor. It's the generic name is rosuvastatin. And I mentioned this before, you know, if you're going into med school or pharmacy school or veterinary school, and you are given the responsibility of prescribing FDA-approved drugs to your patients, a lot of them have certain class names, and the suffix or the ending of that class name. So for instance here, it says statin. So statins are anti-lipidemics, and we saw one of these already with Lipitor. So this has sort of some commonalities with Lipitor. So it inhibits HMG-CoA reductase. And HMG-CoA reductase is an enzyme, and we saw before sort of this spaghetti-looking model here. That's a really huge biomolecule. It represents an enzyme, and an enzyme is a reagent in your body that catalyzes an organic transformation. So what it does, it takes this molecule here. This is 3-hydroxy-3-methyl-glutaro coenzyme A. So this molecule, when reacting with this enzyme, produces methylonic acid. You can sort of see this outline, this carbon backbone at the left-hand portion of this molecule. So methylonic acid is subsequently transformed through more enzymatic steps into cholesterol. And so what Crestor does, this is the structure of Crestor, rosuvastatin, it inhibits this enzyme that forms methylonic acid. So you lower the level of that, it cannot go on to produce cholesterol. This is the company that produces the molecule. So here's what it looks like. I said, you know, sometimes the name is actually stamped on the pill, and then this appears to be the dose, the number here. So I would say 20 milligrams or 40 milligrams. So one thing you want to understand, you know, in society today, there's, especially like in a presidential election year, a hot topic is always about the cost of prescription drugs and why they're so expensive. So in my estimation of what I know in terms of science, they're really not that expensive. But the general society probably doesn't have that same understanding. So again, this molecule Crestor, you can't cut a tree down and isolate it from a tree. You can't dig into a mountain and mine it and isolate it. It does not exist in nature. It has to be synthesized in a lab. So if you look at, you know, if a patient's taking 40 milligrams of this a day, and you can do the math, if they have to take one dose of 40 milligrams per day, times that by 365 days in a year, you come up with grams. How many patients are taking this? So you probably end up with metric tons of material, and you think about the facilities needed to produce that. It's quite a lot of resources. So in its peak year, it sold $7 billion, lifetime sales over $50 billion. And again, that may seem like a lot, but the cost of the research and development that goes into this is quite a bit as well. So the companies are in business, obviously, to make money, and that money supplies future funds for R&D to make newer, better drugs. So So Elizabeth says they just overcharge on life-saving medicines because they can. People overpay or they die. So I'm gonna dispute that. Again, the companies, they have to make a profit to have funds to do future research and development. So are they making excessive profits? Again, I don't think so, because it costs a lot of money to do this research. So when you're in your 255 lab and you're actually running a reaction to isolate something, look around you, look at all the stuff you're using, the facility you're in, and consider like that on an industrial scale, where seriously metric tons of this material have to be produced. So it's even more so involved with vaccines, because vaccines are the hot topic now for COVID-19. If you think about the industrial production of a vaccine, it requires massive facilities to produce millions and billions of doses. So let's answer some, or ask some questions here about Crestor. So which of the following functional groups are present in Crestor? So take a look at the molecule. You're visually identifying functional groups and then associating them with the name choices for the answers. So we could probably spend all lecture debating about the cost of pharmaceutical drugs. And so Elizabeth's point about it being cheaper elsewhere is really, it really is not cheaper. It's just the government subsidizes it more, so the patient doesn't pay as much. There is no such thing as free healthcare, as they say in Canada or wherever. Those people, their citizens, are taxed at a much higher rate. So as such, they have cheaper access to things. So nothing in life is free. So by the responses, it looks like A is the best choice. Again, let's go through here. We have a carboxylic acid in this part of the molecule. We have some alcohols. They end up being secondary alcohols. So here's the carbon bearing the OH group. It's bonded to 2 carbons. So yeah, that's a secondary alcohol. Here's an alkene, carbon-carbon pi bond, and then here's a benzene ring right there. So the other choices basically have a functional group that's not present. So there's no tertiary alcohol, there's no amine, and there's no ether in this molecule. So here's one. What's the molecular formula of Crestor? So you're counting all the different types of elements present and how many of those atoms for each. So while you're considering that, just as a brief aside, I worked in the pharmaceutical industry for about 6 years. In each company I worked for had a research campus, probably the size of USM's footprint. So I mean, these are big campuses that carry out this research. So if you think about the cost of a prescription drug and the cost of, say, a Ford Mustang, no one gets upset that Ford charges, $30,000 for a car, but they do get upset when pharmaceutical companies charge what they do for their product. So yeah, I believe C is the correct answer. So let's go through and do a carbon count. So we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22. So that gets us between C and D for the choices. Because we have 20 and 21 for A and B. So let's do a hydrogen count. So methyl, that's 3, 3. So methyl, that's CH3, right? So 3, 6, 9, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28. And so right there, we've ended up as C is the correct answer. What is me? Is this a philosophical question? You know, it's methyl. So Me is methyl is an abbreviation. So there's 1 fluorine, 1, 2, 3 nitrogens, 1, 2, 3, 4, 5, 6 oxygens, and 1 sulfur. So how many degrees of unsaturation are present in Crestor? And again, this is a visual inspection. So as Garima and Aiden point out in the chat, there are a lot of abbreviations that you're going to have to know for organic chemistry as we move on and we communicate structure. So I see more D answers. D as in dog popping up. So yeah, it's 12. We have 2 rings, which you sort of see there right away, those 6-membered rings. So yeah, it's pi bonds plus rings. So we have 2 rings. Then the pi bonds, we have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So 10 pi bonds, 2 rings, that gets us 12. And again, you know, we're building on these concepts because the rings, the pi bonds, that's how we differentiate how things are hybridized. And we'll see when we start looking at NMR data that carbon atoms and hydrogen atoms occur in different regions in those types of spectra. So given the molecular formula C22H28 F1 N3 O6 S1 for Crestor, how many unique type of carbon atoms are there? So what this question is asking you, really it's about carbon NMR, and we're conceptually thinking about it now, and we'll start looking at the data and what the experiment actually is. But we've determined there's 22 carbon atoms total. What this question is asking you, of the 22, how many of them are unique? And so another way of phrasing that, if they were all different carbon atoms, then you would have 22 different carbon atoms. But there is not. So the answer is it's not D. So the reason why it's not D is because there's symmetry, which renders some of the carbons the same. So the number decreases from 22. So I can't really do anything about screen glitching. Maybe an internet issue. So let's wait for some more responses before we go through this, because I want everyone to really sort of put an answer in the chat So they've had an attempt at it. So from the looks of it, it looks like we're sort of having a debate between choice A or B. So Blakely, one thing you can do is, you know, as you're counting them, like put like a little dot or an asterisk or something to or if you want to use numbers, however you want to do it, to sort of that be your count. So I think from my recollection when I did this, the correct answer is B as in boy, but I can't write on my computer screen. Well, I would say just draw the molecule out real quick on a piece of paper. So let's go through this. I think it's 19. And so the point I'm trying to make here is that, you know, you'll see carbon atoms that may look the same, but they are not based on their environment. So I'm going to start on the left side of this molecule and just scan my eyes to the right. So I see methyl, CH3, but I see another methyl, CH3. Are those two methyl groups the same? So some immediate responses say no, and that is correct because this methyl group is bonded to a sulfur, and that methyl group is bonded to nitrogen. So yeah, they're different, right? So we have 1, 2. Here's a carbon, that's 3. Let's stay in this ring, 4, 5, 6. Now let's go up here. So we're at 6 so far. Let me write that down so I don't forget. 6. Look at this group here. You have a methyl group and a methyl group. Are those the same type of methyl group? So some answers popping up already say yes. Yes, they are. So how do you know that? So if you were standing in the middle here on this methine and you looked out, you would see methyl in methyl. You look down, you see the same. So these all have the same relationship as you look around. So these two are reduced. Instead of counting them as 2, we count them as 1. So we're up to 7 now. So 7, 8. Then let's go down to this ring. So let me write down 8 so I don't forget. Yes, because of symmetry. So look at just this ring. There are 6 total carbon atoms in this ring. Should we count them as 6, or what number should we count them as? Blakely says, how do we know which way we're facing? You have to face all ways, all different ways, all different scenarios. So to answer Elizabeth's question, it is you're looking at the bond line and you're looking at symmetry. What may be confusing you is that, again, the way that structure is shown on the screen, it is a static image, but all these bonds are rotating. Every bond is moving. So this methyl group, this bond rotates. So this methyl group ends up over here. This methyl group ends up over there. So there's rotation. So Blakely is asking, how do I separate video from the chat? Can anyone answer that? I'm not really sure. click on the chat again. Okay, so the question was how many, there's 6 carbon atoms, how many should we count? I think saw a couple answers of 4. 4 is the correct answer. So if you're standing right here where the mouse is pointing, you see that carbon atom bears no hydrogens, right? So that's 1. When you look out here and you look out there, you see the same thing. So instead of counting those as 1, 2, we just count it as 1. You look now here, you're standing here, you look there, you're standing here, you look there, you see the same thing. So those are counted as 1. They're different than these though, right? Because the relationship, this is right next door, this is 2 doors over. So we have 1, 2, 3, and then this one's different because it's bonded to fluorine, so that's 4. So the point I'm trying to make here is that even though all these carbons are sp2 hybridized, they reduce the count from 6 for a couple of reasons. These don't have any hydrogens. These each have 1 hydrogen, but they're different due to their relationships wherever you stand. If you're standing here, those are the same. These are the same. So we can reduce that count from 6 to 4 due to symmetry. And so we'll talk a lot about symmetry this semester. So I think we're up to, that was 8 plus 4, we're up to 12, 13, 14, 15, 16, 17, 18, 19. So the correct answer is 19. So I want you to understand that, you know, if you look at this carbon here, that carbon there, they're both bonded to OH groups, but they're different carbons. And they're different because they don't have any symmetry involved. Hopefully that's clear. Any questions before we do the next one? So sort of the same thing. Now we're asking about the unique types of hydrogen. How many unique types of hydrogen do you see? So remember to count hydrogens that you see on heteroatoms as well. So those count. So we'll let a couple more people answer before we get into it. Again, symmetry will hydrogen is a bit different from carbon in the following sense because, you know, an sp3 hybridized carbon can have 3, 2, 1, 0 hydrogens attached to it. So again, we're still looking at symmetry, but we're going to use the term hydrogen sets, or so that's what we mean by unique type. So how many different sets are there? So will the hydrogen types differ between two methyl groups because they're bonds to different elements? So Katie is asking about, say, two different methyl groups. So let's answer that right now. If we're looking at these methyl groups that are abbreviated ME, are those unique sets of methyl groups? What do you think, yes or no? Yeah, so those are unique sets. Again, they're bonded to different elements, so that makes them unique. So we have 1, 2. Now let's go up here. There's no hydrogens on this ring, right? So we don't have to worry about that. So we're up here now, this group. You have methyl, methine, methyl. These methyl groups, would they be considered one set or two sets? So yeah, they would be one. Again, that's due to symmetry. So we have 1, 2, 3. Then this is 4, right? It's a CH group. It's different from anything we've seen. So we're up to 4. Now consider this ring. Only 4 of the 6 carbon atoms have hydrogens. So how many sets are present in this ring? So I see a couple 2s in the chat. Yeah, so these are the same. So that's 5. These are the same. That's 6. So Blakely, I was asking, there's 6 carbon atoms. 2 of them do not have hydrogens. The remaining 4 do. So there's 4 total hydrogens, but how many sets are there? It ends up being 2 because these are the same and those are the same. So we're up to 6 now. Then look at this pi bond, this alkene. You see this hydrogen here and this hydrogen here. Are those hydrogens the same type of hydrogen? We have 3 yeses. Does anyone disagree? We have 4 yeses. So we have an H here and an H there. The hydrogen's bonded to the pi bond here. So there's 1 here and 1 here. Are those the same type of hydrogen? So we initially had some yeses. Now we have no's. So what is the reason why they are not the same? So again, what we are getting at, even though both of those hydrogens are bonded directly to an sp2 hybridized carbon, they are different types of hydrogen. So why are they different? So as Aiden points out, there's no symmetry. So yeah, if you're standing right here and you look out, you see that hydrogen. You look this way, you see that ring. You look that way, you see that other sp2 hybridized carbon with its substituents. Now, if you're standing here, you see that hydrogen, then you see the rest of this chain. Then you see this other sp2 hybridized carbon of the pi bond. So the fact that when you're standing on either of those and things look different, that means they're different. So what count are we up to now? 1, 2, 3, 4, 5, 6. We're up to 8, 9, 10, 11, 12, 13, 14, 15. So yeah, when you're considering like this thought experiment, like you're standing on, yeah, the correct answer is B as in boy 15. When you're considering this thought experiment of you standing on that carbon backbone looking out, and do things look the same? If they look the same, there is symmetry. If they do not look the same, they are different and there's no symmetry. So if you have a model kit, you know, a model can actually help you with this type of problem. This is the type of model kit I use. You might have something different. I like these because they're nice and small. But this sort of helps as well, because then you can you can touch it. You know, there's learning value in touching things. You know, a tactile response. So these are nice thought experiments, and again, that gets to proton and carbon NMR, which we'll look at in a little bit here. So Aiden asks, is there a way to relate unique hydrogens to unique carbons, completely unsaturated carbons, and unique heteroatoms? I would say there's not like a formula you could so-called memorize. You know, really these type of questions are just about you understanding the concepts and thinking through it. So I would say think of it as a puzzle. There are some thought processes you can go through, but there's really no formula that says X equals A plus B or something. At least not to my knowledge. So let's, I have a couple slides on IR spectroscopy before we get into the continuation of what we did on Wednesday. And again, these are slides that are taken from my screencast that I have yet to post, because I had some issues with my iPad and getting the movies uploaded onto my computer. But anyway, infrared spectroscopy is an instrumental technique that is used for the identification of functional groups. So spectroscopy deals with electromagnetic radiation, and that may sound scary, but the light that you see bouncing off my forehead here, that is radiation. So light is radiation. It's just another term. Spectroscopy is the interaction of light, which is electromagnetic radiation, with matter. So if you're going to take the MCAT, this is going to be a big deal with you, because this is a substantial portion of the organic chemistry section on the MCAT. So we all know this equation here, E equals mc squared. So that's energy is equal to mass times the speed of light squared. So here is the wavelength. So as the wavelength, you know, if we define the wavelength from, say, trough to trough or crest to crest, the longer that wavelength, the lower the energy. So if you think about like radio waves, you know, you're I don't know if people do this anymore, you're driving in your car, you're listening to the radio. Those are really long wavelengths. They're really low energy. So they really don't have any detrimental effect, I would say, on the human body. But as we scan from right to left here, you see that wavelength decreases, and that means the energy increases. So if you look at the corresponding type of wave at the other end of the spectrum, cosmic or gamma rays, the wavelength's really short. That's really high energy. So you're probably all familiar with X-rays from having an X-ray done at some point in your life. If you broke a bone or you had a bad cough and they did a chest X-ray, those are really high energy. And when you get an X-ray, it's like boom. You hear the click, and they take the X-ray photograph pretty fast. If you were to stand in front of that X-ray machine for like an hour, you'd have some bad mojo happening, because what that X-ray is doing, it's such high energy, it's knocking electrons out of the orbits of the atoms in your DNA, and that's really bad. So yeah, the relationship between energy and wavelength is an inverse relationship. So in the spectrum here, radio waves are at the low end. You get the microwaves, that's how you heat up your food. The microwaves hit the water that's present in your food. They start moving really fast. That makes the food hot and tasty. Then you get into IR, which we're going to study. So that stands for infrared. Then you have the visible. So that's what we see from IR. Infrared. Infra means before. So red, Roy G. Biv here. That's what I learned in grade school about the rainbow, Roy G. Biv. Then you get the violet, ultraviolet. There's a movie, Ultraviolet. Pink Floyd, great band. Listen to this, change your life. So UV, X-rays, cosmic rays. So in this class, we're going to deal with primarily radio waves, IR. So IR and radio waves are what we deal with when we look at NMR. So when we're in the infrared region, what physical phenomena the light is interacting with matter is the dipole moment present in a functional group. So you remember when we were talking about the difference in electronegativity between two elements in a bond, and we could assign partial negative, partial positive, and then write a dipole. Well, the IR light has the energy required to perturb that dipole. And so what that means is that it leads to bond vibrations. And so let me just give you a brief sort of recollection of what a bond actually is. So what is a bond? So on the x-axis here, we have internuclear distance. So that's the distance, if you consider my fists as two H atoms. If we're really far away, so the right side of this slide exists but unaware. We have two hydrogen atoms. They exist in space, but they are unaware of each other. So that's you and your significant other at some point in life. They're out there, you don't know they exist. As you go from right to left, you see those H atoms getting closer. They get closer and closer, and eventually they bond to one another. So see these unpaired electrons? We pair them, we form that line. That line means a bond. So in this well, that's what we call the average bond distance. And so if we go up from average bond distance, then we go over to the y-axis to the left here. That's the bond energy. So those things are living apart. They come together to form a relationship. They have a distance between them. In that bond now, there is an energy to that bond. So it's a happy place. So as we move from right to left, eventually the distance between those things, if that was 0, they would be right on top of each other. Notice how this curve goes up. The bond energy goes up, that leads to repulsion. So if you've ever had a bad breakup with your significant other, it's due to repulsion. You know, they leave their toothbrush on the sink and you can't stand it, that's repulsion. So what you want to take away from this curve is that even though we're saying average bond distance and you may get like a static number, the bond actually exists in this well, meaning the bond is not a fixed distance. It's moving back and forth because even at absolute zero, where there's no energy, there's still something called 0-point energy. And that means these bonds are still moving back and forth. So while we report an average bond distance, it's moving around in this well. So the distance between them changes, the bond energy gets a little bit weaker and stronger. And that motion is like the motion of a spring. So that leads me to the next slide here. Bonds are springs. In spring is the time for good vibrations. So we got the Beach Boys here. We got Ted Nugent, Intensity in 10 Cities. So IR leads to perturbation of the dipole moment. So that bond dipole moment, as the light hits it, it makes it either intense or weak. So I'm going to play you a little movie here. Hopefully you can see it. So when we're looking at IR spectrum, these are the different modes of vibrations that occur. So there's symmetric stretching. So I've been sitting on my keister for a couple hours now. I want to stretch. Symmetrically stretching now. So if I do this, Frank the Tank, this is asymmetric stretching. I'm in the mosh pit. Now I'm wagging. Both are moving. Twisting. So remember 3rd grade gym class, the laundry, you're doing the washing machine here. Now you're scissoring, cutting a piece of paper. Now you're listening to Beach Boys here, you're rocking. So these are the common vibrational modes that the dipole moments can undergo. And so when you're actually seeing a stretch in the IR spectrum, that's what's happening to the molecule. So we saw these different functional groups. That's why I keep asking you, what functional groups are present? So if we look here in this column, there's the different types of bonds. Here's the average bond energy, and this is where you start seeing the stretching frequencies. Remember, I talked about the regions these things would occur. 1, 2, 3 are the fingerprint region. So you can see that due to the spring model, lighter elements occur at higher stretching frequencies. And so as we get stronger bonds, the stretching frequencies go down. So you can see from say a carbon-carbon pi bond, we have a stronger bond energy. The stretching frequency goes down as compared to like a CH bond, which has a weaker bond and a higher stretching frequency. So again, I'll explain this stuff in the screencast when that eventually gets posted. Let me go through these regions again. Region 1, Region 2, Region 3, fingerprint region, which we're ignoring. Region 1 is XH, so carbon H stretching, OH, NH. Region 2 is your triple bond stretching, and region 3 is your double bond stretching. So we're looking at this problem, and I'm going to click back over to the document camera, where you were given this prompt. where basically the mass of the parent was 72. We have this signal here, which belongs to a carbonyl. That gave us the clue there was one oxygen. We came up with the molecular formula C4H8O. We then proposed these. Can you guys see these different structures? These were our claims. These are the isomers. So the C4, these are all linear. Butanal, that's an aldehyde. Butanone, that's a ketone. The branched, that's C3. 2-methylpropanal. So now I want to connect that piece of data with the following. So I call this putting it all together, determination of possible isomers from spectral data. This top piece of data is called a Proton Nmr Spectrum. It runs from 0 to 10 parts per million. Let's go through these and do the unique carbon count, the unique types of hydrogens, and then the ratios of the hydrogens. Then we're going to look back at this data, the proton data, the carbon data. The carbon data also has parts per million, but it runs from 0 to 220 in terms of the chemical shifts. So let's do this thought experiment first, then we'll look back at the data that's presented. So for butanal, how many unique type of unique sets of hydrogen do you see? So Blakely's in Brady Bunch mode. She needs to get off it. Again, someone could help her out there. So yeah, there's 4. We have 1, 2, 3, 4. So of the four sets, what is the ratio of those sets? So yeah, if we just, I'm going to say it don't matter which order we write it in right now. We're just, let's say it's 1 to 2 to 2 to 3. So this order does not matter so much. All we're doing is just figuring out sort of the ratio of the sets. Let's do the same for 2-butanone. How many unique carbon atoms do you see? How many unique sets of hydrogen atoms are in 2-butanone? And then what's the ratio of those? So we have 3, 2, 3. And again, this order I'm writing them in really doesn't matter. Now let's do the same thing for the branched isomer 2-methyl propanal. How many unique carbons do you see?
Can you move it down a little bit, please?
Oh, yeah, sorry about that.
Thank you. Thank you.
So the numbers I just wrote in here are basically explaining how you would name this thing. So this is carbon 1, this is carbon 2, this is carbon 3. At carbon 2, there's a methyl group. So these methyl groups are the same, so there's 3. How many unique sets of hydrogens do you see? So this is 3 as well, and then what's their ratio? So if anyone could help Blakely out with visualizing things in the Teams and the chat. So yeah, this is 6 to 1 to 1. So here's 3 and 3. That gets you your 6. There's 1, there's 1. So through this thought experiment, look what we've done. Granted, for the linear case, we had 4 and 4. But for the branched case, this differentiates it. It's 3, right? Here we had 4 sets, 3, 3. So even though this is 3 and 3, which is the same, the ratios are now different, right? So let's go back and look at the screen. Look at this proton data, this Proton Nmr. So Katie asked, when I numbered these carbons, why didn't I number that one? Just briefly, what I did was I looked at the longest carbon chain. I counted that 1, 2, 3. This thing that occurs outside is called a substituent. This is the carbon that methyl group is bonded to, so that's why I didn't number it. So let's look at this Proton Nmr data, and what I'm gonna point out to you now is, see this signal here. I'm counting, even though there's 1, 2, 3 lines, I'm counting that whole thing as a set. So I have 1, 2, 3 sets. So when I look at that data, I can say, okay, the data that is shown is not this compound, because that has 4. So it has to be either this one or that one, because it's 3. And again, all I'm looking at is, I see 1, 2, 3 unique signals. Then you see these numbers I have in red here, 30, 45, 45. So 30, 45, 45. We're going to use that as ratio. So this sort of gets back to Gen Chem when you're determining a molecular formula. If I take each of these and divide by 30. 30 divided by 30 is 1. 45 divided by 30 is 1.5. 45 divided by 30 is 1.5. So we really can't have decimals. We need whole numbers. So we multiply this by 2 because that's going to get us 2, 3, 3. Now look at these numbers. Which ratios does this match? The 2-butanone or the 2-methylpropanol? Yeah, this means divide by. I know we're going a little bit over time, but just give me a few more minutes if you don't mind. So in the chat box, from this Proton NMR data, we used those ratios. We're basically figuring out from these numbers what the ratios are. So it's 2, 3, 3, and look, that's what we found here, right? So using that data, we can eliminate that the data shown. It's going to be the data that is shown is 2-butanone. So what you did in your mind through determining the unique sets, then the ratios, is actually what's being shown in this piece of data. We have 1, 2, 3 unique peaks. Then the ratio is 2 to 3 to 3. Now let me ask you another question, and this is sort of, I know we're over time, but if we could just continue the thought process here. If you're looking at the structure, let me redraw it. You're looking at this structure. We said we had 4 unique type of carbon. So we have some resolution here, right? Of the 4 unique type, 3 are sp3 hybridized, 1 is sp2 hybridized. We have further resolution of this.
Thank you.
Okay. So we had 4 unique type of carbon. 3 are sp3 hybridized, right? 1, 2, 3. 1 is sp2 hybridized. But we have further resolution of these, right? We have 2 CH3 groups and 1 CH2 group. So now when you look at this spectrum back on the screen, the one that's 30 is CH2 group, right? Because we said the ratio is 2 to 3 to 3. So this peak at about 2.5, 2.5 ppm belongs to the CH2 group. Now look at the remaining peaks that belong to 45 and 45. What do you think this one where my mouse is pointing to? I'm going to renumber the carbons. 1, 2, 3, 4. Where my mouse is pointing, we've already assigned carbon 3 to 2.5. So now we have 2 methyl groups remaining. The peak at chemical shift of 2 belongs to which carbon atom, 1 or 4? So the peak at 2 parts per million is a CH3 group. The peak at, sorry, that's 0.8 parts per million is another CH3 group. How do we differentiate these two in terms of an assignment? So this one right here, does it belong to carbon 1 or carbon 4? So where did these numbers come from? See where this peak is right here? I'm just looking down. See this number? If this is like 2.5, I guess I'm a little bit wrong. This is maybe like 2.5 there. This is maybe like 2.4 or something. So see how these two are close to one another? If we said that the peak at 2.5 belonged to the CH2 group here, that CH2 group, see how it's next door to this carbonyl? See how this CH3 group is next door to that carbonyl? So the peak at 2 must be carbon 1. And then the peak at 0.8, this peak, that must belong to carbon 4 then. Does that make sense? I know that was sort of a crash course in interpreting Proton, and again, we're going to go through this in more screencast and chat sessions. But really what we're trying to do is make sense of how we can look at a structure, think about uniqueness, and then assign it to actual data. So please take a look at your homeworks, 14 and 15, and your Orion sets. Over the weekend, if you have time, I'll post those screencasts on Mass Spec and IR for you to view, as well as this chat. If you do have any questions, shoot me an email, and I'll try to respond as fast as I can.